Hello everyone, this is Dr. Feng Wang again. This is the second part of my review for OChem 2, starting from chapter 14, conjugation. Conjugation, I would like to say, conjugation is the Mr. Trump Tower. So basically, electrons, pi bond electrons that can move in a bigger space. So the requirement is for at least you have a 3 or more p orbitals. They have to be adjacent to each other. So if you have one here, you have another one here, they are not adjacent to each other, you are not going to have a conjugation. So why we have a conjugation system is because electrons, they always want to have a bigger place to move around. So whenever you have a p orbitals, they are perfectly parallel to each other in adjacent atoms. Does not have to be a carbon atom. Right? The definition, it just says atom. In this case, the pi electrons can move around in a bigger space, which reduced the energy level of the whole molecules. And that's why the molecules prefer to form a conjugation system. So whenever we have a conjugated system, particularly for alkenes molecules have a unique UV and visible absorbance. So the longer the conjugation is, the longer wavelength. Either this is UV light. Sometimes if we continue the conjugation, we can move into visible light region actually. So the longer the conjugation is, the longer the absorbance of the UV light. So the unique reactions from a conjugated dienes, we learned thermodynamic, and we learned kinetic products. So at an extremely low temperature, so the kinetics products is the major product. At a high temperature, the molecules prefer to form a more stable product. This is a more stable. Basically, it's a thermodynamic product. This is a more stable alkene than this one because of the more substitutions around the alkene functional groups. Another very, very important reactions in this conjugation chapter is Diels-Alder reaction. And this is a unique reaction to form 6 membrane organic molecules. Now, I told you many times 6 is a very magic number, not only to organic chemistry, but to other natural product. So basically, we have a conjugated alkenes react with a single pi bond alkanes here. We are going to form a 6 membrane molecules. And this is the alkene. All we have, this is the Diels-Alder reaction always forms the alkene carbon-carbon double bond here, plus a 6 membrane. That's the unique features of a Diels-Alder reaction. If the two substitute in the alkene on the same side of the double bond, in the final ring structure, the two substituent will be on the same side. They are all dashed line or wedge line. These two molecules, basically the same molecules. So if you cannot figure out why these two molecules are same molecule, it's just the way we draw it differently. But essentially, they are the same molecules. How you turn these molecules around, flip around to have this structure, I think this is very good practice. So one more thing I want to say about this molecule, this molecule is a meso compound. It's a non-chiral molecule. Why? It is a meso compound. This is another very important concept that we learn. from OCHEM1. So another feature for Diels-Alder reaction is for the bridged Diels-Alder reaction product. The bigger group Z is preferred in the endo position. We have two options here. So if this would be the reaction, we have two product. But normally the endo, the Z far away from the bridge point is preferred product, also the major product. Another product is the less preferred product in the Diels-Alder reaction. So then we move to aromatic molecules. This is basically aromatic molecules, special conjugated molecules. And basically, if we have a molecule that meets the four requirement, is we got a new group of molecules, so we call them aromatic molecules. The first one, the first three, basically, the first two requirements are very simple. It has to be cyclic, well, when I say cyclic, does not mean it has to be carbon in the circle. It could be carbon, could be nitrogen, could be oxygen, could be other atoms. The requirement is cyclic, not carbon cyclic. It's cyclic. So the second requirement is planar. So all the aromatic molecules, they have to be planar molecules. But I don't have much requirement for planar. So even in the exam, I normally tell you it is a planar structure. If I don't tell you, or other professors don't tell you, you just assume it is a planar structure because this is so complicated. So the third one, the third one I think is not easy. So it has to be a completed conjugated system, which means each atom in the ring has to provide an sp2 is an sp2 hybridized atom, which means this atom has a final p orbital, and the final p orbital is not hybridized, so they can be parallel of each other perfectly, so the electrons can move around because each atom provides an orbital. I didn't say each atom has to provide an electron, one or two. So the requirement is that each one has to provide an orbital. So the next one is Hankel rule. Hankel rule basically is the requirement of the electrons, the number of electrons in the ring structure. It has to be 4 times n plus 2. N is just a whole number. It could be 0, could be 1, could be 2, but it's not negative. It's not a half number like a 1.2 or 1.5. That does not work. N has to be 0 and a positive whole number. So if we meet this 4 requirement, then it is aromatic molecules. We learned how to decide a molecule if aromatic or non-aromatic or anti-aromatic. Then we move to next chapter, the reactions of aromatic molecules. The first important or very popular reactions of aromatic molecules called an electrophilic substitution reaction. Basically, we generate positively charged species because it's positively charged, or full positive charge or partially positive charge. So it's going to react with the electrons in the aromatic ring. So to do a substitution reaction is called electrophilic substitution reaction. And this reaction we learned in the video, many individual reactions like halogenation reactions, with the catalyst or in halide. The nitration reaction normally use the sulfonic acid as the catalyst. And the sulfonation reaction is also another electrophilic substitution reaction with the sulfonation reagent, the forming sulfuric acid or sulfur trioxide along with the sulfonic acid. So another very important reaction is called a Friedel-Crafts reaction. So first, the Friedel-Crafts reaction is the alkyl halide react with the aromatic molecules to the alkyl. Basically, we introduced alkyl group into the aromatic ring. It's the second Friedel-Crafts reaction is called acetylation reaction. Basically, we introduce a ketone molecule. Introduce a ketone groups to, link the ketone groups with the aromatic molecules. Both reactions requires a catalyst, and normally we use the Lewis acid catalyst, aluminum chloride, very good, very popular catalyst to do alkylation reaction or alcyl. This is alcyl groups. Alkylation reactions of aromatic molecule. There is a or there are some limitations for Friedel-Crafts reaction. One of them is very popular one. If we have a very strong electron withdrawing group on the aromatic ring, we would not have a Friedel-Crafts reaction. The second very important reaction for aromatic reactions is called nucleophilic substitution reaction. In this case, if we have a very strong nucleophiles, we have a very good leaving groups. Normally it's halogen. The first case is if this aromatic molecules also have very strong electron withdrawing group, we can have a nucleophilic substitution reaction. Or even without a very good strong electron withdrawing group, at least we have a very good leaving group, and if we have a very strong nucleophile, we can also have a nucleophilic substitution reaction. So this is just the two mechanisms, and I hope you have a little bit of time to review, the two different mechanisms for nucleophilic substitution reactions. This is a very important table. It's about the directions of the aromatic reactions, particularly for the electrophilic substitution reactions. So I don't have much to say about this table, but the expectation is at least you should remember, some common ones, like ketones, amines, hydroxyls, or ethers. Other aromatic reactions, we can do the bromination reaction of this is the alkene aromatics, this side aromatic, this is the alkenes. When we do the bromination reactions with the radical mechanism, actually the alpha carbon, the first carbon attached to this, the benzene ring is brominated actually. It's not the benzene ring, but the alpha carbon is brominated. If we do the oxidation reactions, and again, regardless of the length of the alkane groups here, we always forms benzoic acid. So the only requirement for this oxidation reactions is you have at least one hydrogen and the alpha carbon. So more reduction reactions of aromatic molecules, ketones can be reduced by different reducing agent, or the nitrobenzenes can be reduced to amines. So the next part is I think is the biggest part of OChem2 is about a carbonyl compound. First, we learned carboxylic acid and amines. We learned different ways, different factors that can cause the increase or decrease of the acidity. So basically, when you analyze acidity, you basically analyze the relative stability of their conjugated bases. The better stability of a conjugate base, the stronger of the acid. So amines, they are all normally serves as a base. So how we analyze the basicity of amine molecules. Basically, we analyze the lone pairs of electrons on the amine atom. So the more electrons densities we have around the amine atom, the stronger the base, because again, base provide electrons. The more electrons that you have, the stronger the base you will be. This is a very, I consider this is like a template reaction. It's a multiple step reaction, but I think there are all simple reactions. So the target of this reaction is to prepare the substituted aromatic molecules. How we make a substituted aromatic molecules? We start from a benzene. We first make a nitrobenzene, then reducing the nitrobenzene to the amine. The amines, when we have amine, we do a diazonium reaction. Basically, amine react with sodium nitrate, and acid condition, we forms the azonium. This is like a salt. So the azonium salt, basically this part is a very, very good leaving group. So all we do from here to here is to introduce a very good leaving group via amine and nitro aromatic molecules. Then the next step is to use a good nucleophile to do the substitution reaction. So basically, we introduce the nucleophile part to the benzene molecules. All right, that's the second part of my review. Then I will cover the final part, the reactions of a carbonyl compound. All right, see you later.